Failure theories. Today we're going to be talking about some of you may have already be familiar with the Tresca criteria and the von Mises criteria. So, yes. So we'll be covering that today and just kind of talking about failure theories in general. And then next week we'll start applying the concept of failure to identifying failure mechanisms. So before we launch into that though, do you have any questions for me on homework due tonight, or anything else that we've been talking about?
Did you explain again the process for number 4? The last one where you have that.
The one with the distributed load?
Distributed load.
Okay, so if I remember correctly, I don't have it in front of me, but
I got it.
you do? Is it a fixed beam with a
Fixed.
roller?
Yep.
There's no overhang, right? It's just
No overhang.
Yeah, okay. All right, and you have your Q there. So because it's indeterminate, right, you have to start by choosing one of the reaction forces to relax and turn into something that you're going to treat as an applied force. So you'll just apply statics and from your equilibrium equations write the other two reactions in terms of the one that you relaxed, right? And then set up Castigliano's method to solve for the reaction at the location where you relax the force by setting up those integrals with respect to the partial derivative of that force, and then set that deflection equal to 0, since you know if you're doing the roller sport, right, you know that the deflection here is 0. You could do the moment at A and then set everything up with respect to the angle or the slope at A, and take the partial derivative with respect to the moment at A. So you could do it that way too. Either way, you'll end up with a result that will allow you to then write all of your reactions in terms of Q and L, right? Then you want to find the maximum deflection in the beam. In order to do that, you're going to have to apply a dummy load, because with the distributed load, we still don't have a discrete point force to apply, right? And so that's what the Castigliano's method is built upon, or the modified method anyway, is built upon a discrete force or moment that you take the partial derivative with respect to, and that point has to be the same location where you are determining the displacement.
Which we don't know, right?
Right, we don't know where that needs to be, so that's another unknown in the problem. So, but you can intuitively conclude that it's going to be in the second half of the beam's length, right? So you can put your dummy load somewhere there, set this distance as an unknown value, and then you're basically setting up that integral to solve for the unknown value, right? So you'll have Q playing into everything, and then since you've already determined the reactions in terms of Q and L, now if you add the dummy load, you're just going to have to update those reactions in terms of the dummy load, right? So another way to do it, like and this is the solution, this is the approach that the solution takes. From the very beginning, you could include the dummy load on the beam and write all of your, do all of your statics, write all of your reactions in terms of Q, Fi, and then whichever support you choose to release, if it's RB, right? Maybe you're doing that one. And then you're still going to go through and you're going to solve the integral with respect to the partial derivative of RB, right? So that just means a lot of things are going to simplify. You won't have the dummy load showing up, but you'll have the equations already set up in terms of the dummy load, so you could do it that way as well. But either way, you're first solving for RB in terms of
Mhm.
the applied load. And if you include the dummy load initially, you'll have it in terms of the dummy load already, right? If you don't, you can just go back and add that dummy load effect in later. And then after you know the reactions in terms of Q and Fi, then you can solve for A.
Okay, so when you apply the dummy load, you would then have to go back and do Castigliano's, but setting the deflection at one side or the other equal to 0. To update your reaction forces. Or do you just look up in a table somewhere, reactions for a prop cantilever, which I don't know.
The prop cantilevers are pretty down. I can't deal with it.
Yeah,
What?
it was on our precast exam.
Oh,
prop
okay.
cantilevers.
Yeah, so, okay, can you repeat your question?
Well, basically, because you add the dummy load, and
Yeah.
this is an indeterminate beam,
Mhm.
so you cannot determine, using statics,
Mhm.
the additional reactions based on the additional load. So would you have to go back through and do Castigliano's once again, setting the deflection at B equal to 0, and then solving for the dummy load?
Doesn't the dummy load count I guess the fictitious, not the RB, I see.
So let me think, so, cause you'll already have RB in terms of Q
L.
and L.
But it needs to be in terms of QL and FI.
Yeah, you want that in there too. So, yeah, I mean, there's a couple ways you could do it. You could do the Castigliano's method again with just Fi and then superimpose the results, yeah. Or you could use a table,
Yeah,
a beam table, yeah.
And superimpose those results, basically.
Mm-hmm, yeah.
Okay.
Yep.
Yeah.
Does that help?
It sounds hard.
Yeah, it's a lengthy and tedious one, but yeah, you have to solve for A and then also solve for the maximum deflection there, so, but that can be done once you know, once you set it up. Yeah.
Okay.
All right.
Thank you.
You're welcome. Any other questions? Okay. All right, so launching into failure theories. Of course, when we talk about failure, there are different limit states that we speak to, right? So we determine a certain limit state that we are wanting our structure or material to reach, right, before we consider it to have failed. And there are different mechanisms of failure, right? They all involve stresses. So some modes of failure include, I'll list a few of them, and then in this class we're really just going to focus on one of those. So you've got fatigue, yielding, buckling, and creep, which is really relevant for just concrete and wood. So in this class, we'll focus on yielding as a mode of failure. A very idealized stress-strain curve, right, just accentuates the point of yield as that location where you lose the modulus of elasticity, basically, right? So I'm going to note that with a capital Y. And the strain associated with that, right, would be the yield strain. The area under the stress-strain curve up to that yield point represents the elastic strain energy. All right, so we've been doing a lot with strain energy. And now we're back to the stress strain curve and just noting that it is the area underneath that curve. So, as you are all familiar with, yielding is when the material transitions from being wholly elastic to not wholly elastic anymore, right? The onset of yielding. And there is usually some sort of transition region that we call the yield region, right? So it's not exactly always a discrete point that's super easy to identify. It will be a specific point, it's just where that line starts to deviate from being perfectly linear. So again, I'm going to note that this capital Y I'm using to refer to the yield stress. And that's going to be determined uniquely by experiment. Specifically, a uniaxial test. And the reason I'm using a capital Y here instead of a sigma Y is because I don't want it to confuse it with normal stress in the Y direction, right? So 3D segment of material, right? We have our 6 total stresses that act on that element. Normal stress in X, normal stress in Y, and normal stress in Z. Also, the shear stress in the XY plane. We have the shear stress in the YZ plane, and the shear stress in the XZ plane. So we've got our 6 stresses, and then if we consider the principal direction, we have 3 principal stresses. All right, so sigma 1, 2, and 3 will be used to denote principal stresses throughout this lecture. And so that leads us to bring Moore's circle back into the game. So if we have our 3-dimensional consideration, right, and we have 3 principal stresses, I'm going to label sigma 1 as one extreme, sigma 3 as another extreme, and then sigma 2 will be the magnitude that falls in between. So if we have it arranged such that sigma 3 is the smallest or the most negative, and sigma 1 is the greatest, the greatest positive or smallest negative, however that might work out. Then the maximum shear stress would be the difference between the 2 extremes over 2, right? You can take the absolute value of that difference. And technically plus or minus, right? So. All right, so this leads us to the Tresca criterion, and I know some of you are familiar with this, may be new to others. The Tresca criterion states that yielding will begin when the shear stress reaches a limiting value, the maximum shear stress. right, where tau max is the largest radius of Moore's circle, assuming the material is isotropic. Further, the failure surfaces will be the planes of maximum shear. So for the uniaxial case, you would only have one normal stress, and that normal stress would be a principal stress, right? So your only principal stress, you would set that equal to the limiting value, the yield stress. The other two principal stresses would be 0. So that means that Moore's circle, right, the radius would be half of the maximum principal stress. So that means that tau max is equal to 0.5 times the yield stress. So for a multi-stress state, all right, if you have, again, our extreme values of sigma 1 and sigma 3, and then sigma 2 in the middle, then the absolute value of the difference between the two extreme stresses divided by 2 would be equal to half of the yield stress. And that's the Tresca criteria. Any questions so far? Okay. All right. So next, I'm going to introduce the concept of average stress, where the average stress is simply the average of the normal stresses for a given state. And that's going to lead us to be set up for the definition of the von Mises criterion. So if we think about a material that is under hydrostatic pressure, right? If it's under hydrostatic pressure, that means that all of the normal stresses are equal. So there is a change in volume associated with hydrostatic pressure. And we're going to use the fact that a material under hydrostatic pressure does not yield. But first, I'm going to define what we call distortional stresses. And these are stresses that contribute to distortion without volume changes. All right, so these would not be present in a hydrostatic state. So that would be any shear stresses. And then any variation between a normal stress and the average normal stress. All right, so I'm going to define the strain energy of distortion. We'll call that capital U with a capital D subscript. And that's equal to 1 over 12G times, in brackets, this is going to be really long, so I'm going to make sure that I have enough space to the right. We have our first term is sigma x minus sigma z quantity squared plus sigma y minus sigma z quantity squared plus sigma x minus sigma y quantity squared. And then we have plus 6 times the summation of the square of each shear stress. So tau xy squared and tau xz squared and tau yz squared. All right, so going back to the hydrostatic state where the distortional stresses are not present, so that would mean if we had all the normal stresses are equal to each other and there are no shear stresses. Then you have no distortion, only the hydrostatic state. Which of course means that the strain energy of distortion is equal to 0. So we're going to define now the strain energy of distortion in terms of a new term that I'm going to call the effective stress of distortion. So I'll say U sub D is equal to 2 times this sigma E squared over 12G. All right, to simplify the above expression, where sigma E represents the effective stress of distortion, and that is going to be equal to 1 divided by the square root of 2 times, I'm not going to rewrite it for all of our sakes, but times this whole thing. And then the square root of that whole thing. All right, so the von Mises criterion then states that yielding begins when this effective stress of distortion reaches a limiting value, all right? Unlike the Tresca criterion, which was just based on shear stress, and when that reaches a limiting value, now we're focused on this whole thing. All right, so the limiting value would be, for example, the yield stress. Though if you were designing to fracture instead of yield, then you would set your limiting value to the fracture stress. All right, so again, we'll start with a simple uniaxial case, right, where let's say your normal stress in the X is the normal stress that's present. Set that equal to the limiting value. All other stresses are 0. So the effective stress of distortion will just be 1 over the square root of 2 times, if we look at the values inside the brackets, all these terms will be 0 and this term will be 0. So we're just going to be left with sigma x squared plus sigma x squared. So since we set sigma x equal to y, the limiting value, that's going to be the yield stress squared, and then square root of that. So this comes out to just the yield stress. So then for a multi-stress state, we can set that effective stress of distortion equal to the onset of yield. And so then plugging it in, we have 1 over the square root of 2 times, in brackets, sigma x minus sigma y squared. Let's see. Well, there's actually nothing new about this line. It's the same as what was written above. All right. Same as above. And that is set equal to the yield stress. If you are just working in terms of principal stresses instead of an XYZ stress state that includes shear stresses, then this will simplify. So you'd have sigma E is equal to 1 over the square root of 2 times sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 1 minus sigma 3 squared to the 1/2 power, and that's equal to the yield stress. All right, so just to quick summarize this page, because it seems like, I know it feels like it's probably all over the place, but we're basing all of this on the fact that a material under hydrostatic pressure does not yield. So if we define all of the stresses that are not included in the hydrostatic state, which are the distortional stresses, and define the strain energy associated with those stresses, then we can use that to define the point of failure, right? Questions? Okay. I know these theoretical lectures are so fun. All right, well, we have a couple of, I guess, qualitative examples. No numbers, but we'll at least think through the process and the equations. So we'll apply, well, first, does anyone still need to copy stuff down, or did I move on too quickly? Good, okay. All right, so we have a sphere with pressure internally, and expose the internal stresses, right? This sigma S is shown as the longitudinal stress. All right, but for a sphere, the longitudinal stresses and the hoop stresses are both the same magnitude, and they're both principal stresses, unless there's some other force at play, right? If there's only pressure involved, then they're both principal stresses. So the normal stress, principal stress that we have, is equal to PR over 2T. And we're going to set that equal to both of our principal stresses in the plane of the material, right? So in the third plane, the third principal stress would be the out of plane direction with respect to the material, right? And that is going to be 0. Or approximately 0, right? For practical purposes, we can say sigma 3 is equal to 0. In reality, it can be a relatively very small number compared to the other two. That just accounts for the difference in the pressure on the inside and then the ambient pressure on the outside. All right, so if we first consider the Tresca criteria and apply that to this thin-walled spherical pressure vessel, we would set the maximum shear stress equal to the limiting value. And back from our Tresca criterion page, right, we landed on this formula right here. So we'll say maximum shear stress is equal to sigma 1 minus sigma 3 over 2, and we'll set that equal to the yield stress over 2. But first we'll calc it out. That's going to be the pressure times the radius divided by 4t. So then we can conclude that the maximum internal pressure to cause the material to start yielding, which we can call Py, is equal to 2 times the yield stress and the thickness divided by R. Now let's see if we apply the von Mises criteria, will we get a different result or the same result? So we'll set up our equation for the effective normal stress. So that's 1/2 times, since we are working in terms of principal stresses, we can use the simplified version of the equation for the principal state. So sigma 1 minus sigma 2 quantity squared. And we don't have a sigma 3, so the other two terms are just going to be sigma 2 squared and sigma 1 squared. Set that equal to our yield stress. And since sigma 1 and sigma 2 are the same, we have 0 plus 2 times PR over 2T squared. And then the square root of that value in brackets. And then solving for the pressure associated with that yield stress, we get 2 times capital Y T over R. So same result. But we will not always get the same result between the two methods for determining failure. So the next example will demonstrate that. If we simply change our pressure vessel from a sphere to a cylinder, now things will get a little bit different. So in a cylindrical pressure vessel, we have hoop stress and longitudinal stress. They're not equal to each other. Who remembers which one is larger?
Longitude, oh gosh, longitude, no, really?
Hoop stress is larger.
Oh, yeah, that makes sense.
Yep.
Because the crack goes like,
Yeah.
I just remember.
You remembered the longitudinal crack and you thought, yeah. All right, fair enough.
Longitudinal stress, but that's not how that works.
Right. All right, so if we consider a segment of the material on the surface like that, right, we have our longitudinal stress, sigma x, we'll set that equal to our sigma 2, and that's PR over 2T. And then the hoop stress, sigma y, we'll set that equal to sigma 1. Since it's the largest, it'll be an extreme. And that's PR over T. And then sigma z, and this is, right, the XYZ notations here, I guess they're consistent with this axis shown above, but that's specific to this location on the cylinder, right? If you had this location, those little XYZ notations would switch up, unless you decide to update your axes accordingly, but just as a reminder. So sigma z is going to be your third principal stress, and that's equal to 0. All right, so first we will apply the Tresca criteria. So maximum shear stress, set that equal to the difference between the two extreme principal stresses. So that's just going to be PR over 2T. And we set that equal to Y over 2. So the pressure to cause yield would then be Y times T over R. The von Mises criteria will write out our effective stress of distortion, so 1 over the square root of 2 times in brackets, and once again, we are working in the principal state, so all we need is the 3 terms associated with the differences between each of those principal stresses. So from sigma x minus sigma z, we get PR over 2T squared. And then from sigma x minus sigma y, we also get PR over 2T squared. And then from sigma y minus sigma z, we get PR over T, and then we'll square that. Take the square root of that summation, set that equal to the yield stress. And then we have the yield pressure is equal to 2 times the yield stress times the thickness divided by the square root of 3 and R. So, 2 different results, right? And in this case, the Tresca criteria gives us a more conservative result, right? Because it's telling us that yielding is going to occur at a lower stress value compared to the von Mises criteria. The 2 over square root of 3 is larger than 1, right? I don't know what it is. It's larger than 1. So the Tresca criteria tends to be more conservative. And for you folks, the mechanical engineers, that you've seen these 2 before, is that consistent with what you have learned in your other classes? Yeah. Okay. Good deal. All right, any other questions?
So these are basically 2 different limits. Like you're going to see failure. You're theoretically going to see failure when your pressure reaches one of these limits. Not like the pressure doesn't have to reach both limits.
Right. So
Before.
you would just like pick one method to use basically for your design and just kind of
And Tresca is generally conservative, or just for this specific case here?
In general, I think there is like certain conditions where the Tresca is more accurate. Does that sound right, you guys?
So,
Yeah,
I don't remember
I
what it is.
Yeah, I don't remember what it is either, but
We were given graphs of like each one in its relation to.
you were
Get stressed, it was cool.
okay.
There's a few different ones.
Cool. Yeah.
Interesting.
Do you
It
remember?
was like, I don't know, it was some like circle thing, and it was like how they did the geometry like around to like calculate.
I don't remember that.
Yeah.
That's too long ago.
So I want to say, and I'm going to double check this, but I want to say that Tresca tends to be more accurate if shear is dominant, but I'm going to double check that and see if
Yeah, it's like
something else.
some weird diagram where Mom, you sees it like this, like the
Oh,
oval,
yeah,
and then
right.
it's like, yeah, it's like the area inside.
Yeah,
Yeah.
that's right. So yeah, we're not gonna get that detailed and that involved in this class, but it's just a general overview of these two methods and what they're rooted in. And then, yeah, next time we're going to apply, actually, I don't know if we get into the Tresca criteria. I don't know if we apply the Tresca criteria to the next lecture. But yeah, next time we're going to look at beam failure. So fun stuff coming up. All right. Well, have a great weekend, everybody.